going to speak today about the connection between gamma ray bursts and supernova explosions. And I will first give a historical introduction to the topic so that you know what we are talking about, and then I will present a slew of new and upcoming results on this work. In a certain sense, the gamma ray burst supernova connection was actually first propagated by Sterling Colgate at a time when no one knew that gamma ray bursts actually existed, except maybe for a few people at Los Alamos National Laboratories who had detected the very first burst with the Vela satellites a year beforehand. So in 1968, Sterling Colgate made a model that predicted that the shock breakout of type 2 supernovae, so those that have red supergiant progenitors, could possibly produce a flash of X-rays and gamma rays at the time that the explosion comes out. Okay, so anyway, in 1973 then, gamma ray bursts were first published by Klebesadel et al. In the famous paper. And for the next 20 to 25 years, people were searching for the progenitors of gamma ray bursts, and this is a time which is usually known as the time when there were more models for GRBs than photons detected, which might be a little bit of an exaggeration, but probably more models than GRBs detected. And then in the early 1990s, with the launch of the Compton Gamma Ray Observatory and the BUTSI experiment on board, there were first hints that gamma ray bursts were cosmological sources due to the discovery of an isotropic distribution of GRBs. So at this time, Stan Woosley made yet another GRB model, which in the end proved to be more or less correct. And he proposed that the progenitors of GRBs are the collapsing cores of very massive stars, which he called collapsars. And in his initial model, the GRB was only produced in the case that the core collapse of the star actually did not produce a supernova. So his prediction was that we would see a gamma ray burst, but there would be no accompanying supernova at all. And then in 1997, the afterglow era was opened with the discovery of GRB 970228 by the Beppo-Sachs satellite, the discovery of an optical afterglow by Van Paradise et al., the X-ray afterglow by Costa et al., and then with the next burst, 970508, the cosmological redshift was found by Metzger et al., radio afterglow by Frail et al. So you probably all know these famous Nature papers from back then. And then in 1998, a very big surprise happened, namely GRB 980425, which was associated with SN 1998 BW. So this burst was discovered by the Beppo-Sachs satellite, and in the error box of the X-ray telescope of Beppo-Sachs, there was a nicely resolved face-on spiral galaxy in which in the next days a very luminous supernova developed, which was named 1998 BW. And the interesting thing about this supernova was that the spectrum was extremely peculiar. So it was quickly seen that the spectrum was deficient in hydrogen and helium lines, which means it was a type 1c supernova. And additionally, in comparison to normal type 1c supernova like 1994I, which has become one of the poster cases for normal type 1c, the absorption lines were extremely broad. And this hinted at very high expansion speeds of the supernova photosphere, about in the range of 0.1 times the speed of light. And this was not the very first broadline type 1c discovered. I think 1997 EF was beforehand, but it was one of the very first cases. And this here is a supernova light curve taken from a paper by Clock-Sciatti et al., who added another large amount of data a few years ago. And one of the aspects of the supernova, which could be followed for a very long time, also with the Hubble Space Telescope, was that it had a absolute magnitude of about minus 19.5, which puts it in the range of typical type 1a supernova and definitely exceedingly more luminous than usual type 2 supernovae. So, as I had mentioned beforehand, Stan Woosley predicted that GRBs should not show any supernova at all. But suddenly we had a very powerful supernova, and in the same issue of Nature that the famous paper from Galama et al. Appeared, there was also a paper by Iwamoto et al. With a model which pretty much coined the term hypernova. And for some reason this has fallen out of, no one really uses the term anymore, so these days we just call them broadline type 1c, which sounds a bit more unwieldy and maybe a bit less sexy, but whatever. So just to mention one short thing, this is a little plugin for a paper of mine that I did basically on the afterglows of long and short gamma ray bursts in the host frame. You can basically ignore almost all of the plot except for this one point here. And this is an upper limit on any kind of afterglow from 98 or 425. And the very main point is that the isotropic energy release of this burst was extremely small. It was and remains today the closest gamma ray burst ever discovered, and also the one with the lowest amount of energy released. And this is an assumption for a spherical emission, which is probably correct, since we don't have any indications that it was strongly jetted. So, as mentioned, GRB 98 or 425 is in no way a classical cosmological gamma ray burst, which means that while people were already relatively sure back then that the GRB, which was detected by Beppo-Sachs, was actually associated with the same event which produced the supernova, this was a bit complicated due to the fact that we were still seeing two different kinds of beasts in terms of the gamma ray emission. Then, actually a bit beforehand, there was a burst, 980326, which was shown by Bloom et al. A year later to actually have a relatively peculiar light curve. So here you can see the classical optical afterglow, which is probably after a jet break, decaying relatively steeply, and then it goes over and becomes flat. And initially people thought this was just the host galaxy of the GRB. But when they observed again a year later, they just found an upper limit, and I think there was later a detection by the HST somewhere down at 28th magnitude. So the actual light curve of the burst shows some kind of rebrightening, and then it decays down to the host. And at this time, of course, the data on 98 or 425 had been published, and Bloom et al. Showed that if you just use a light curve similar to 98 BW, you can, at roughly a redshift of 1, model the light curve of the entire event. One problem is that spectroscopy on this burst was not successful, so there is no redshift known from absorption line spectroscopy. And they actually tried to also do a redshift spectroscopy of the very late time source, but this is basically just noise. So this seemed to indicate, because this was a normal GRB, that there was also a connection between the more classical GRBs and supernovae. And in the late 1990s to early 2000s, more and more examples became known. So these late-time bumps at low significance were found for several more GRBs, including actually, in retrospect, for the very first one, which had happened at a redshift of 0.7. And for the first time, several GRBs exhibited these bumps detected in multiple colors, and it was found that the colors of these bumps were significantly more red than those of the afterglow, which indicated that the spectrum was roughly thermal, Planck-like, which would also be indicative of a typical supernova photosphere, compared to the afterglow, which is just a power law due to synchrotron spectrum. There were also several attempts at spectroscopy, so GRB 11121, which I mentioned beforehand already. There was spectroscopy published by Garnavich et al. They did detect a continuum, but no supernova features. And I actually think this is quite interesting that this continuum is rather blue. So this is something maybe we should keep in mind for something I will talk about later. There was an very faint X-ray flash, or 20903, which also showed an actually quite decent spectrum, which for some reason I am not quite sure was only published in 2005. So a long time after an event, which I will soon talk about. So this was a bit lost in history. And there was also 021211, where another low signal to noise spectrum was found, but interestingly this was at a redshift of 1, so this was quite an achievement, and it kind of looks like a supernova spectrum due to the very broad lines, but there's not really much visible. And then in 2003 came the burst that has been known as the Rosetta Stone, 030329 and 2003 DH. So this burst was a very, very luminous burst, one of the brightest bursts detected by the Hetty mission. And it had an extremely bright optical afterglow, which was followed up by hundreds of telescopes. And it was found to lie at a redshift of 0.17. And some days after the burst, spectroscopy showed a quite clear signal of a broadline type 1c supernova. This was originally discovered by the Ohio State people from Chris Dunek, but then Jens Hjort decided to write a Nature paper on it. So in some sense he got more fame even though he wasn't the actual discoverer of this supernova. And for the first time after 98 BW, a nice spectroscopic sequence could be obtained. And despite the fact that the afterglow of this burst was very bright and in some sense covered the bump that you would normally see, in spectroscopy it showed up very well. And this burst was definitely energetically similar to cosmological GRBs, but it was still relatively faint in terms of intrinsic terms and also a relatively soft GRB. So there was still a difference between this event and, say, famous events like 990123, which showed this 9th magnitude optical flash and was much more energetic and much harder. Just a few months later, surprisingly, another nearby low luminosity GRB was discovered, which also showed a spectroscopic supernova, 031203, and SN 2003 LW. And this was a point when people started discussing that there might actually be another population of gamma ray bursts, which are energetically much less luminous than the cosmological ones, and which we can only detect at relatively near low redshifts. In 2004, shortly before I was already doing my diploma thesis here at the Thüringer Landessternwarte in Germany. My predecessor, Andreas C., and my boss back then, Silvio Klose, published a paper in which they had systematically studied the data of all optical afterglows known at that time. And in the case of low redshift, and in this case I mean redshift roughly less than 0.7, they used a model of SN 1998 BW as a template and found that in all of these bursts that actually had late observations, such red bumps could be found, which could be modeled by SN 1998 BW and were roughly in the same luminosity range. And so what they did is they introduced the parameters K and S, and K means the peak luminosity of the supernova in units of 1998 BW luminosity within the certain band. So this is like more of a relative value, and the S is a stretch factor, which means that the light curve of 1998 BW can be stretched or compressed in time while keeping the general shape. And it was found that all of these supernova bumps could be modeled in case these two parameters are additionally introduced. Yes, Omar?
What was the properties of the gamma ray burst that accompanied these bumps? Were it like normal gamma ray bursts or no luminosity value?
No, they were, with the exception of 98 BW itself, these were all classical GRBs up to redshifts of 1. And actually the number of 0.7 was simply introduced because there was one case, 980703, where no bump was found. But there, the extinction along the line of sight was very high, so it could be quite easily shown that the actual supernova would have been much fainter than the host galaxy and couldn't be extracted out of the data. And a few of these cases were quite bright GRBs. Some of them were less bright, more in the 030329 range, but all of them were at redshifts of 0.3 and beyond.
Variable. Variable.
What do you mean?
Gamma ray bursts were variable, not a single peak.
Most of them, I think, were quite variable. For example, 011121 was, for the most part, it had, I think, a late kind of like X-ray flash, but for the most part was a Fred peak. But there were a bunch of different shapes. Yes?
Do you mean that The afterglow and the do you mean that the afterglow and the supernova stretched by the same amount would
No, the
match?
afterglow is fitted separately.
I see.
By either a power law decay or a broken power law decay. And okay, maybe I should have shown a nice figure here. But for example, in the case of a 11121, this was very nicely separated. So you had like a decay like this, then it broke down and went under the host galaxy magnitude, and then it showed a nice bump. So you could separate the two very well. And yeah, okay, so in the next years, some further cases were added, but nothing really special, including another low signal-to-noise spectrum for Massimo della Valle. And also, I started working together with the Tautenberg people, and we presented the first results on host extinction-corrected supernova light curves. And then in 2006, we got another very interesting event, XRF 060218, and this was shown to be an extremely long but very soft gamma ray burst with a peak energy of just a few keV. So basically the band function was peaking in the X-ray band of SWIFT, and SWIFT detected this very, very slightly varying emission for almost 2,000 seconds before it had to slew away. And additionally, the UVOT telescope discovered what is attributed by Campana et al. To be an ultraviolet shock breakout flash of the supernova. So the first part you can see here, this is not labeled very well, but basically this is the most ultraviolet band of SWIFT. So this shock breakout was actually brightest in the ultraviolet. So the spectral shape was basically the exact opposite of what you would see from a gamma ray burst afterglow, which becomes more luminous toward the infrared. And then it switched over into the supernova, and as you can see, this down here is the V band. So the V band was relatively faint in the shock breakout, but then was among the brightest filters in the supernova, whereas the ultraviolet in the supernova decayed very strongly. And this burst was observed extensively with a spectroscopic campaign led by Elena Pian. And I was actually also on this paper, and it was interpreted in another paper by Paolo Mazzali. And what you can see here, these black lines are synthot fits with different elements to the spectrum. And in this case, it was actually found to even be very oxygen deficient. So Mazzali proposed that this was a type 1D supernova, but I don't think that ever really caught on. And additionally, there was the idea that the whole system was actually powered by the spin down of a magnetar and not by a classical black hole. And the one thing is, this burst was also very close. At the time, it was the second closest, well, actually still today, the second closest GRB. And again, it had a very low luminosity. And then in Tautenberg, we presented the optical follow-up in terms of photometry of the supernova, and for the first time did a large comparison with the overall GRB SN sample known so far. And so I had explained beforehand what this luminosity factor K is, and this is just K plotted against redshift. So all the way down here we have 060218, which was a bit fainter than 98 BW at peak. This line of 1 equals 98 BW. And here you can see the two other nearby bursts that I mentioned. This one low luminosity, this one moderate to high luminosity, this one low luminosity, and all of these up here were at least moderate to high luminosity. So starting roughly here is the range of classical GRBs, with this one exception that was very close. And as you can see, there doesn't seem to be any kind of relation between redshift and the peak luminosity of the supernova. Additionally, if you were to plot these against the isotropic energy release, you would not find any kind of relation.
Are these redshifts corrected, or are they independent of redshift? I mean,
This is well, it's not really independent of redshift in the sense that the band we are tracing here is basically always the observed R band, because that's where most telescopes are most sensitive. But intrinsically, these supernovae are becoming more and more blue because of the redshift. So the bluer radiation is redshifted into the R band. So I will say something about that later too. So it's not completely correct to compare all of these. And now this is a plot which will also show up again later. This is the luminosity factor versus the stretch factor. And the dots with open symbols are not corrected for extinctions, the other are. And as you can see, at least here, there's no kind of real correlation visible. Okay, so next followed another few years of more incremental progress. There was one very interesting event at the beginning of 2008, which I have called an X-ray outburst, because it has actually been shown that it was not relativistic at all. And this was an extremely interesting discovery in the sense that there had been a Type 1b supernova, as in 2007 UI, at the end of December 2007 in a galaxy called NGC 2770, which was being observed by the Caltech team with SWIFT at the time. And they wanted to do X-ray and UVOT observations of the supernova, and suddenly in another part of the galaxy, they saw a supernova explode at the exact moment that they were observing. And this created an X-ray flash, which was a few hundred seconds long before basically fading back into obscurity. And a few days later, an optical transient was found, which was actually shown to be Type 1b, not Type 1c. And it is possible that what we have seen here is actually a true transition object between Type 2 supernovae, so those which still have an envelope, and the low luminosity Type 1c GRBs. So basically, we don't see any kind of relativistic emission at all, but there is a kind of X-ray flash, which is roughly that what Stirling-Colgate predicted in 1968. And after that, we see a Type 1b supernova, which has not removed its helium envelope. There was the famous naked eye burst, 080319b, which back at that time was the most luminous GRB detected by the SWIFT mission. This was followed up at late times, and a red bump was found by Tanvir et al. Here's another one with a moderate signal to noise spectroscopic association. Then this one was also relatively similar to 030329, but at a higher redshift. And at this time, for the first time, Berger et al. Took a spectrum of the host galaxy at late times and used this to subtract it from the supernova spectrum to get better calibrated results of the supernova, and especially more confidence that they were actually seeing supernova emission and not just some strange SED of the host galaxy. And finally, in 2010, there was another event which was very similar to XRF of 60218. And this was also spectroscopically followed up very well, including multicolor follow-up at many epochs with a ground camera in La Silla, and I was also part of this study. So, let me do a first summary here. So what we know by this time is that long GRBs, at least those that are close enough to observe, and likely by inference all of them, are associated with the core collapse of massive stars. The likely progenitors of these GRBs are Type 1 Wolf-Rayet stars, which are those which are probably associated with Type 1c supernova. And I'm saying probably because actually no one so far has discovered the progenitor of a Type 1c supernova. And with this, I don't mean a gamma ray burst associated one, but just a normal one at very low redshifts. There was actually a paper a few months ago about a new Type 1c in the antenna galaxies, and they had HST data, but they actually didn't find a star. But the limits that they discovered were actually disagree with those for a red supergiant, but a Wolf-Rayet star would be fainter in these bands. So it's likely that this associative chain is correct, but we don't have like shooting gun evidence yet. Furthermore, the supernova associated with GRBs have exceptional expansion velocities, which creates these broad lines. One of the problems up to 2010 was that most of the high-quality spectroscopic associations were those with non-classical GRBs, and the classical GRBs were those that had very bad spectra because they were much farther away. And the basic two exceptions are these two GRBs, but as I had mentioned before, they are quite X-ray rich and only of moderate luminosity. And now I will talk about some new results. So the first GRB I want to talk about is 11-1209A. And this burst is extremely exceptional because it is the longest gamma ray burst discovered so far. The duration of this event was about 25 kiloseconds, which is something around 7 hours, which is quite a difference in comparison to the typical bursts that are maybe 20, 100, a few hundred seconds long. So this is the light curve from the Konus wind detector. And any of you who are working with prompt emission, if they look at this light curve, they would immediately say, yeah, looks like a typical relatively high luminosity GRB, multiple episodes, some sharp peaks and everything. And if this were like 100 seconds from here to here, no one would remark about it. But if you look down here, this is minus 15,000 seconds and this is plus 15,000 seconds. So the duration of this event was extreme. There's actually something that might also be associated here at about minus 10,000 seconds, but it's unclear. But we can be quite sure that the burst started about 5,000 seconds before the Swift trigger. Swift followed this event up in X-rays for a long time. And what you can see up here in front is basically all prompt emission over several Swift orbits. And then it goes over into this well-known phenomenon of high latitude emission, where the X-rays decay very steeply and become very soft, and then goes over into a small plateau phase, and then finally a normal afterglow at late times. So in many ways, this looked like a classical GRB, except that it was about 100 times as long. There was a lot of discussion about this event, if it might be a tidal disruption flare, where a star basically gets torn up by a supermassive black hole. But I think the evidence definitely points to a normal gamma ray burst. And, well, you can't see very much here, but I am working on a paper which is mostly finished on this burst. And what you can see here is the database of this paper. And everything starting from here up to here is data from the Grunt camera, which is a special camera which observes in 7 colors simultaneously, mounted at the 2.2 meter telescope in La Silla in Chile. And the burst was actually relatively close to the horizon in La Silla when it happened, so we were unable to observe immediately because it was under the pointing limit of the telescope. But we started the next night, and actually instead of finding a typical decaying afterglow, we got a plateau, which then exhibited a very steep rise. And in the second night, it was still the same magnitude and then began decaying. And the other data is from the UVOT telescope from Swift, and it becomes kind of messy over here. But one thing I might want to point out is that the white band data, which was observed until close to 30 days after the burst, shows a very clear color evolution. So at this time here, it is just in my offsets here, just a little bit fainter than the G band data, and then it becomes significantly fainter down here. So what we are seeing here is actually a spectral color change in this very broadband filter, which shows the occurrence of a supernova. And you can't really see it here very well in this plot, but there's a clear bump here in the other filters. I will show more about that soon. So this is a plot of all the data I have access to at the moment. These were some early observations from the Tarot telescope in La Silla, which was able to point much lower, which shows some very rapid variability during the prompt emission. And additionally, from Levin et al., there are observations mainly in the J band up here, and in the U band with both Gemini and the HST. And I'm very happy for these U band observations because they are so far in the ultraviolet, especially in the rest frame, that we basically don't expect any supernova contribution here anymore. And this just shortly is the best that I can make of what the optical transient without the supernova looks like. So you have a lot of variability up here in the prompt emission, which goes over into seemingly a normal afterglow decay, the strong rebrightening. Maybe another bump and a rebrightening, but I'm not sure because this is UVOT only, and then goes over into this normal decay, which then becomes steeper, exhibiting a jet break. And this now is a fit of the late time data, in which I used the U-band data as a pure afterglow to model the underlying afterglow, and in the other bands you can very clearly see the bump of the supernova going all the way into the J band. Though I should mention this J band is roughly the I band in the rest frame. And one very interesting point is that this is about 80 days after the burst. This last observation, and back here is the host galaxy 1 year later.
So you have a supernova bump 80 days after the burst.
Up to 80 days. I mean, the peak lies at about 25 days after the burst, which is around here. So, one study I did in my paper was to take all of the data of the bursts that we had beforehand and actually do a study of the supernova in different filters And I mean, there's a lot of detail hidden here. One of the things is that these are these plots of K versus S for the single supernova for different GRBs. And one of the things you can see is that in most cases they are relatively close together, which means that the spectra are similar to those of 1998 BW. But 11-1209A shows a very big difference. So down here is an S factor of 1, and the K factor of 1 is actually outside of the plot. So the supernova is more luminous than 1998 BW in all bands, and especially in the ultraviolet, which is the observer frame G band, it goes up to 5 times more luminous. And so this is a very crowded plot with all of the results from beforehand plotted in. And the main thing that you can see is that 11-1209A basically lies outside of everything else. And another thing I want to point out is that now with this large mass of data points, you can roughly make the statement that there seems to be a relation that slower supernova are more luminous, roughly. And this brings me, okay, so just a quick summary. Basically, I've told you all of this. It's probably the most luminous GRB supernova discovered so far. And since I think I saw in Leo's talk that in the transient space he will also show superluminous supernova, which have been discovered in the last few years, this one doesn't count yet. So especially in the rest frame R band, it is about, we haven't really computed it yet, but it's about minus 20.2 or so, which is more luminous than typical GRB supernova, but is not yet in the definition of real superluminous supernova. And the thing is that we are the only people who actually have data that really show this supernova. And other authors, because no one had reported anything in the GCN, assumed that there was no supernova, and due to the extreme length of the event, decided that it must be due to a blue supergiant progenitor, which could possibly produce such very long GRBs. And I think we have evidence to show that this is not the case. Levin et al., at least in their data, found a reddening. And they also have spectroscopy of this burst, but interestingly enough, it doesn't show any real supernova signatures in the spectroscopy, only a relatively red continuum. And there was also some theoretical modeling by a Japanese group, which tried to fit the late time data from Levin et al. With a model of a cocoon photosphere that exists after the breakout from this blue supergiant. And I think if they were to compare their model with the data that we have, they would see that it doesn't really work out. So all in all, I think 11-1209A, despite its extreme duration, is likely to be a normal GRB with a stripped envelope progenitor. So the next one I want to talk about is 120422A. This is a paper that is being prepared by Steve Schulze. And this is likely a missing link between the low luminosity GRBs that I showed beforehand and the classical GRBs. So this burst was at a redshift of 0.28, and it was already suggested by Binbin Zhang et al. That due to its relatively moderate luminosity and spectral properties, it was basically a link between the two populations that were maybe thought to be separate beforehand. Melandri et al. Already published a relatively small paper with some photometry and spectroscopy, and Schulze et al. Are preparing a paper with not just optical photometry and spectroscopy, but also radio observations, X-ray observations, host galaxy observations, surrounding of the host, and a lot of other things. So it's like 26 pages long already. This is a quick plot of the supernova. So at early times, there are some evidence for a shock breakout similar to 06 or 218. And then you get a kind of an afterglow component which decays and goes over into a very clearly visible multi-wavelength bump. As mentioned, there are also lots of spectra were obtained with quite high quality. And now this is a quite interesting plot, and I'm saying it's preliminary because we will probably be adding more data to it. This is again the K versus S plot, but in this case we are choosing only those points which are roughly equivalent to the V band in the rest frame, so that you can actually have a direct comparison. And here again, you can see that there seems to be a rough relation between the duration of the supernova and the luminosity. And the one that we are talking about is right in here, and 111209A is not in here, but would be somewhere up here, basically still following this relation. So this burst has already been mentioned. In April, the brightest gamma ray burst in 29 years occurred, and for the first time, we have actually seen what we would call a real cosmological GRB, full energy GRB, at a very low redshift, namely 0.34. And this burst was highly variable, as you can see, with an extremely bright spike lasting over 100 seconds. And these plots are from a paper from Dan Purley, which I was also involved with. And this also shows a spectroscopically confirmed supernova, which was detected by the Gran Telescopio Canarias and has been published by Dong Su et al. As you can see, the quality is not terribly high. One of the main reasons is that the host galaxy of this burst and the afterglow were quite bright, so it was a bit hard to disentangle the two things. But the supernova is definitely in existence. And it's also seen photometrically, so this is a plot from Dan's paper. It looks quite ugly. The main reason for this is that at the moment we simply don't have perfect host galaxy magnitudes yet to do a subtraction, because the burst simply is not old enough yet. So we're going to have to wait until sometime late this year to obtain host galaxy observations. Okay, so now for some final quick notes on upcoming studies of bursts. The next paper I'm going to be writing is on a burst which happened exactly 2 days after the other one. And this one was detected by the Agile satellite and is the first GRB supernova associated for a burst from Agile. And this also had an SN, which was spectroscopically discovered by the GTC, and we have good coverage from the ground camera monitoring it photometrically. GRB 130215A is for me a bit special because it's my birthday burst. And interestingly enough, this event is actually even a bit fainter than 120422A. And again, the Gran Telescopio Canarias got the spectroscopic supernova. I don't actually know much yet about the photometric cover because this is being prepared by Zach Cano, and he was still analyzing and compiling data and everything, so I haven't seen any light curves yet. This burst is also still much in preparation. Another one, which might be as one of these transition events at moderate redshift. A supernova was discovered photometrically by Grant, and then we followed up with a DDT program at the VLT and also got it spectroscopically again. The spectrum is not terribly nice, but it definitely shows supernova features. But this was too far away to do a really detailed study. Then just some days ago, well actually just over a month ago, there was a very interesting GRB, which is actually the most interesting part. It is that it shows an X-ray plateau followed by an extremely steep decay, which is probably a signature of magnetar energy injection, which then turns off. This one was at a redshift of about 0.5. The supernova was discovered by our Russian colleagues with the Majdanek Observatory, and I'm not really sure about spectroscopic follow-up of this one, if it exists or not. And finally, really just a few days ago, there was an extremely interesting burst, 130925A, which was another ultra-long duration event lasting at least 15,000 seconds about, at a redshift closer than the other one. And the problem is, we actually observed this during the complete prompt emission with a Grant camera. So we were on it a few minutes after the burst, and like after 2,500 seconds, the main emission came while we were still observing. The problem is that the afterglow is extremely extinguished. So this is basically the highest extinction ever measured along a GRB line of sight with a very high confidence. And therefore, it is completely unclear if we will, in any form or fashion, be able to detect a supernova for this burst, because we've predicted that it should be about 25th magnitude in the J band or something like that at peak. And finally, my honorable mention to Leo. He will talk more about this event later. This was an extremely nearby GRB at a redshift of 0.15, so actually even a bit closer than 030329. Which was discovered through extreme computing power, you might say, with an intermediate Palomar transient factory in a gigantic error circle. And the interesting thing is it didn't turn out to be just some run-of-the-mill GRB that they had discovered, but an extremely peculiar event. And this one was also with associated with a spectroscopic supernova, originally discovered by the KNOT and confirmed by several telescopes. And I've already heard that Bradchenko is working on a paper on the supernova spectra, and I'm assuming that the Danish group with a KNOT will also be writing something. I put this as an honorable mention because I am, for one, not involved in any of these studies, while everything else I was presenting beforehand I'm somehow involved with. Okay, so anyway, from the new results I have presented, first of all, there is this class which might be some kind of new class of GRB, which Levin et al. Called ultra-long duration events. And it seems we have evidence to show that these are also associated with the core collapse of massive stars, though we don't have a really good case yet because this one was at too high a redshift to get really good spectroscopy. Then it seems that there are several events in the last years which form a missing link between the well-known and well-studied low luminosity GRBs and the classic cosmological GRBs, and these are also associated with supernova. And then 130427A, the closest ever truly cosmological GRB, shows that these are also definitely associated with broadline type 1c supernova. And a final mention, since the topic of this workshop is basically new missions to new science in GRBs, in these last years you will have noticed that the GTC has shown up quite a lot. The spectroscopic follow-up of supernova has become more intense and we have gotten a lot more hits. So in the years beforehand, we maybe got one every 2 years, and then there was a nearby one where we got a lot, but it was a peculiar GRB. And now finally we are getting at least one spectrum for almost every burst at a redshift of say 0.6 or less. And in all cases, they always look like SN 1998 PW, maybe a bit shifted, like for example in this case, which is much more ultraviolet luminous. But we're kind of catching up with the whole thing. One sad piece of news is that Antonio de Ogato Postigo actually doesn't have his program anymore at GTC. I don't really know why, it was not approved anymore, so at the moment maybe the rate is going to go back down again. But yeah, so there's probably within the next 1-2 years there will be a lot of publications coming up on spectroscopy of GRB supernova. Okay, thank you.